Hello, we have been taking up questions on circles with theorems applicable to arcs and angles obtained by them. We continue with more theorems under that. The first one I write here is the angle in a semicircle is a right angle. That's a very simple one. I draw a circle here, as because they talk about semicircle, we'll draw the diameter here. This is the center of the circle, and we just name this point of intersection as PQ. And where is the angle in the semicircle? Either I draw it on the part, you can also draw here this side the angle, and we name this point of intersection to be R. What is given to us in this figure? We write here. We are given that PQ is the diameter of a circle with center O, and this angle, which is POQ, is an angle in semicircle, right? What do we have to prove is angle PRQ is a right angle, that means a 90-degree angle. We know from previous session and the theorems as well that the angles obtained by an arc of a circle at its center is twice the angle drawn on the remaining part of the circle. That means this angle POQ is twice of angle PRQ. I can write refer theorem. We get angle POQ is twice of angle PRQ. We also been said angle POQ is 180 degrees. So this is equal to twice of angle PRQ, thereby making angle PRQ as 90 degrees, right? So we got PRQ as 90 degree. That's what we were supposed to prove. Let's move on with another theorem which I can draw here. We'll just be taking the converse of this theorem. I can take up with the same figure. I write the theorem here though. The arc of a circle subtending a right angle at any point of the circle in its alternate segment is a semicircle. Oh, I made a spell mistake there. I am taking up the same figure. Herein it is said that this arc PQ is subtending the angle PRQ as 90 degree, and we have to prove this PQ as semicircle. We here take the same application of the theorem, which reads as the angle subtended by an arc is at the center is twice the angle formed by the same arc on remaining part of the circle. So angle POQ is twice the angle PRQ. So angle POQ will be twice of 90, which is given to us. That makes angle POQ 180 degrees. thereby making it as a straight line. If that's a straight line, that means PQ is a semicircle, right? We move on with another theorem. It reads as angles in the same segment of a circle are equal. This is quite helpful to solve questions based on these theorems. It gets applicable to almost every question based on them, on these theorems, or based on the arcs and their angles subtended. I draw this figure. Now this figure can be drawn in two ways, just to show that they are drawn on the same segment. Suppose I take up this as the center. Here also I'll take O as the center, but the way we draw the two figures will be different. Herein I take one as a minor, the other one to be the major. I can take this as the minor one. This becomes the segment. And here I can take this as the major one, and I mark them whichever I'm taking. This one, here I'm taking this one. How are the angles drawn on these segments? I draw one here. This we can name as PRQ. We can also draw another one here, which might just be intersecting the circle at the point PQRS. And this can be one figure. I better write the center O here, and can erase this one. I draw again the similar figure, but this time the figure will be drawn based on the major arc. This may be, and we name this as P, this is R, this is S, and that's Q. We have already named this as O. Now the same, whatever explanation we take up for this theorem will remain same for both the figures given. We know that the angle drawn at the center subtended by this arc will be twice the angle which is drawn on the rest of the circle, or the remaining part of the circle. So in both the cases, let's take up the first one. Maybe I'll just use the first figure, and then same for the second figure as well. So angle POQ can either be expressed as twice of angle PRQ as well as twice of angle PSQ. So we can equate this one, the right hand sides of the both equations. So twice of angle PRQ equals twice of angle PSQ, thereby making angle PRQ equal to angle PSQ. So these two are equal, which is drawn on the same segment. The same thing we can write and just see how it applies to the second figure. When we talk about POQ, that means we are referring to this reflex angle, which is twice of PRQ. When we say POQ with the same is equal to PSQ, sorry, not equal to, it's twice of PSQ, thereby again making these two angles which are marked to be equal in the second figures. You followed it, hopefully. Move on with one more application. Now we move on to application, not any more theorems. I draw a figure. This is the center. There is another angle which is subtended on the remaining part. This point of this is given O, This is marked ABC. This angle is given to be 40 degree. We have to calculate angle AOC. That's the question mark. Okay, this is also informed to be 30. How do we do this? If I join this OB as well, you see in triangle OAB, OA is equal to OB, thereby making the two opposite angles is equal as well. Angle OAB will be equal to angle OBA, thereby making this angle 30 degree. So angle OBA is 30 degree. We can write here 30 degrees. Look at the other triangle, in triangle OBC. Similarly, OB will be equal to OC, thereby making angle OBC equal to angle OCB. So angle OCB was 40, so angle OBC will also be 40 degrees. So this is also 40 degrees. Now the whole of angle ABC is equal to angle OBA plus angle OBC, thereby making it 30 plus 40, and that's 70. We know that angle at the what do we have to calculate? Okay, we were supposed to calculate AOC. Okay, AOC is twice of angle ABC with the same theorem applied as we just did in the previous two screens. We said that the angle drawn at the center by an arc is twice the angle subtended on the remaining part of the circle. So AOC will be twice of 70, that makes 840 degrees. But not much difficult. Move on with another application of these kind of theorem, these few theorems we have already discussed. I again draw a figure. Give me a couple of minutes wherein I take to draw the figure. This is one angle which is marked as BAC, and the other which I'm drawing right now, this one is marked as BDC. This is BA. This point of intersection is marked as E. This is D, and this is C. The information says this one is angle 130 degree and this given to be 20 degrees. We have to find, let me write, find angle BAC. If I mark it using some other color, it will be this one. If we see BED is a straight line and one BEC is given to be 130. If you mark this one, BED is a straight line, this one is marked to be 130. So this part of it, that one is angle CED. Angle CED is equal to 180 minus 130, and that gives us 50 degrees. Alright, so that one is 50 degrees. Now in this triangle, small one CDE, let us understand why we are doing this. We are doing all the process to find this angle, which is actually equivalent to angle BAC. Why? Because angle drawn on the same segment are equal. Now look at the triangle. In triangle, the small one CED, what do we get? Angle CED, plus angle EDC plus angle DEC, that is 180 degrees. Angle CED we calculated to be 50. EDC we will be calculating, so let it be as EDC, and plus DEC. Oh, I made a mistake here. No, yes, I don't think this is the right name. It should be ECD. It should be ECD. Just excuse me, I'll write it again correctly. ECD, and the value of ECD is 20. That's equal 180 degrees. So angle EDC is equal to 180 minus 70. That's giving angle EDC as 110 degrees. If EDC is 110, angle BAC will also be 110, because EDC is equal to BAC, and here you can write angles in the same segment are equal. So angle BAC is also 110 degrees. Thank you.